Kia ora. This is a great little simulation for you to explore your equilibrium principles based on concentration and how it relates to reaction rates, and comparing K, which is the equilibrium constant expression value, and Q, which is worked out in exactly the same way. It's just simply not at equilibrium yet. But if Q is equal to K, then it is at equilibrium. So here we've got a parking lot with the same number of cars each, and I have the same reaction rate forward as well as back. So if I start my reaction, this is an equilibrium. My forward and reverse reaction rates are identical, and my overall concentration of cars or number of cars in my parking lot B or products is the same as in parking lot A. Or it simply doesn't change. It remains that, and this one remains that. They do not have to be identical. So what happens now if I reset the reaction and I say, right, there's a sale going on here, so we're going to have more cars wanting to go to and visit parking lot B. So I'm going to move that forward reaction rate going to B to 1. Now notice that K is now 2, whereas Q was still 1 based on the previous example. So in order for Q to get to K, I must increase it. And the only way is to increase the numerator, or the number of products, or the number of red cars, or decrease the number of blue cars. So if I start the reaction, notice that I had a lot more of a forward reaction going, and then that rate slows down as I have fewer and fewer blue cars, and I get slightly more of a reverse reaction as I have more and more red cars. And, so let's do that again because I changed that start reaction, and you'll see that it will eventually reach equilibrium where Q increases as there gets more and more cars over there until it equals 2, which means the system is now in equilibrium. So I can do the same thing with a reaction. So here's H2 plus R2 going to 2HI. Now that should be H2 plus R2. There are a few glitches in this. As I say, don't worry about the actual calculation here. Just compare the values. So here Q is smaller than K. So in order again to get Q equal to K, I need to increase my products or decrease my reactants to get Q to be bigger, because the numerator at the top, if it's bigger, makes the value bigger. So if I start this reaction, then notice I had more of a forward reaction, but as I get fewer particles over here, the reaction rate slows down until the forward and reverse reaction rate are the same, and you'll see now they are in equilibrium because Q is equal to K. If I reset this reaction and I say, what happens if I have now lots of starting material but no products? Okay, so K is still the same because I haven't changed the temperature. Now I've got to start the reaction and pause it just so you can see the changed Q. I've got very few reactants, so Q has become very small. Sorry, very few products, so Q is very small. So in order to increase Q to equal to K, I need to increase the products to make it bigger. And so you'll see my forward reaction is very strong in the beginning, but as my number of particles decrease, I'm not going to have such a fast forward rate, and my reverse reaction rate is going to increase as I have more reactant particles. So if I press play, you'll see this one increases, that one decreases until it is more or less the same. And this looks at the concentration, and you'll see when Q is equal to K, then the concentration of the reactants don't change, or the products don't change, and the concentration of the reactants don't change, even though the actual individual particles are changing all the time. Then finally, I can also explore this system. Here Q is bigger than K, so in order to make Q smaller, I have to increase the reactants or decrease the products. In other words, the numerator must become smaller and the denominator must become bigger. So if I start the reaction, then notice the reverse reaction was more, but it decreased as I had fewer and fewer products until the reaction rates are the same, and now Q is equal to K. The system is at equilibrium. I can again say, okay, what happens if I have lots of products and no reactants? And notice that K doesn't change. K, because I haven't changed the temperature. Only the temperature changes K. So if I start the reaction, I have a big reverse reaction. But as I have fewer particles there and more reactant particles, eventually the reaction rates are the same. And you'll notice in Q eventually gets to K. So now the system is in equilibrium. And I can do the opposite as well as I did last time. I could have lots of reactants and few products. And if I start my reaction, it goes the other way. So have fun exploring. Kia ora.